So here we are now. This is a transmitter circuit, the schematic. So here we have a HT12E encoder, and then we have a RF transmitter over there, and then we have a voltage regulator. It is a L78L05. It's 5 volt regulator, and then we have a shunt regulator as well. So you can actually make it this way or this way. Okay, I use 10K, 220K, I think, as a voltage divider. I like it more this way, so everything is fixed, and also try to make this thing to be small, and so I use this way. I prefer this way. Okay, then we have 10 ohms and a LED there. So there's the IC here. It operates from 2.4 volts to 12 volt. Okay, but the problem here I had is that the RF transmitter, it does not work beyond 5 volt. Okay, that's why I used the 5 volt regulator. So I'm gonna be powering this thing with the 12 volt batteries, the small ones, and then using voltage regulator is going to reduce to the required voltage for the transmitter and this circuit here. Okay, I added this sense over here of this shunt regulator. It is a low voltage LED indicator. The circuit here, it's working from 2.4 volt to 12 volt. Below that, it won't work anymore. This setup here, 10K, 220K resistance, acting as a divider. The setup makes sure the voltage, when it drops below 2.5, 2.6, the LED here will turn on. Okay, the LED here will turn on. So the 10K, 220K, acting as a voltage divider, the voltage drops down, the LED turns on, indicating the battery has to be changed, or the battery is running low. Or you can also use this way, using a potentiometer to adjust the required voltage. But I like this one more. Everything's fixed. Okay, so that's all about it. It's not really complicated about it. But I'm gonna go ahead and show you on a breadboard how it's all working. Okay, so here we have the transmitter itself. So voltage here, we have the RF transmitter, the IC here. Okay, HT12E encoder. I have a button here. I have a cell battery here, and then is a low voltage indicator. Okay, so I'm gonna go ahead and hook it to the bent power supply, so you can see how much voltage is using and how much amps is also using. So I'm gonna, okay, let's see, ground there. Okay, and the LED is turning on. So as you can see now, the LED is turning on at the 3 volt. Okay, and then if you see, the amps is 0.019 milliamps. Is really not really much, but so this thing is working from 5 volts, so I'm gonna go there to 5. So 5 volt is drawing around 0.037 milliamps. That's not really much. So then when the voltage, if I reduce the voltage here, if you watch closely, we are not at 3, you go to 2 volts, 2.6, and then 2.5 LED turns on already. 2.5, 2.2 is nothing, because also the LED is gonna start lighting from I think 1 volt something of 2 volt. So from there, 2.6, 2.5, the LED will turn on. Also 2.4 also will turn on. And so remember, the circuit here, it cannot work below 2.4 volt. So when the LED turns on, it should change your battery. Okay, so it's a very useful circuit, and you can see it's very compact, small size, transistor size. So that's all about it. There's not much into it, but I'm using now a switch here, but actually this thing is gonna be transmitting continuously. Okay, so and there will be no switch required actually, and the LED here will turn on when the battery runs low. So that's all about that transmitter. So I'm gonna go ahead and show you the receiver side. Okay. So here is the receiver circuit. So this is a schematic of the receiver. The main what the main I see here, it is a HT12 decoder. Also coming along with the CD4027 acting as a flip-flop. So I press button here, it's the IC activate, it goes high, giving an output here, and it stays that way of wait until it get the second signal to go off. So I press one time, it goes on, stays that way. I press again, it goes off and stays that way. Okay, and this is gonna be the manual mode. And then we have a ref receiver over here. Okay, and this is gonna drive send the signal to the HT12 decoder. Okay, decoding the signal from the encoder. The IC the voltage from the IC works from 2.4 volts to 5 volt DC. And then here we have an LD here and a resistor there to indicate when the signal is present on the IC here. Then we have a diode here. You have 10K capacitor, 10K here again, and then the transistor there. The 10K here, the 10K and the capacitor here is ensured to discharge slowly. Okay, that's why the 10K is there, to discharge this capacitor slowly. So meaning it's gonna give kind of a 5 second delay to turn off. Okay, and then we have a photo over here. Okay, then we have a transistor to drive the relay over there, and then we have an LED here. So when the relay is on, the LED turns on as well. And then we have a diode here, and then you can see polarity how it is drawn here. So meaning that it will block any voltage wanna come back to the transistor over here. So this is really useful to be there. It should be there, must be there. Otherwise you're gonna spoil your the transistor over there. So that's all about it. And also here as well, the circuit here is also working from 2.4 to 5 volt DC, but the RF receiver here, the maximum voltage is 5 volt. Okay, I got to power the whole thing with 10 up to or 12 volt, but it's impossible. It's gonna burn things out. As you can see here, it's 12 volt here, then it's 5 volts and 5 volt. So I also use a voltage regulator to regulate the voltage here to give the right places the right voltage. So I'm gonna show you the breadboard here. Okay, so here is the circuit itself. So we have a flip-flop here, and then you have a receiver. We have a HT12 decoder, the big capacitor over there to discharge slowly. We have a photocouple over there, and then a transistor to drive the relay, diode, and then LED indicator. When the relay is on, the LED turns on as well. Along the relay there, we have aside the relay we have a voltage regulator there. Also small package there. It's kind of nice working. You can shrinking your project in a small. Others have to use a big voltage regulator, and then it's not really necessary on this circuit. So the small one is better to use there. Okay. So and then as you can see on my voltage on my bench power supply, so we are now currently at 10 volt and about the 0.005 milliamps, and this is now like standby mode. Okay, is using not really much of the amps there as well, but when I press the switch here, it's activating the relay and the circuit here. You can see the different voltage is gonna rise up. Okay, so you can see then the voltage is rising there up. It's 10 volt and then 0.053 milliamps. Okay, I switch off again, and then it drops down to 0.5 milliamps. So it's not really using much of the power of much of the amps. So it's a very simple and nice accurate circuit. So I press the circuit here, turns on the fan there, and it waits until the second signal again. I press again and it goes off. Okay, so this is one part of it using the manual mode, or you can use the transmitter. Okay, so this is the transmitter circuit. So I'm gonna connect the battery over here. So the way I designed this circuit here is going to be when I power the circuit, is going to be transmitting continuously. Okay, like so. So you can see it's just transmitting, and then LED is turning off. But let's say you work out of range of your battery is running low. I'm going to disconnect here, and then you're going to see, so this disconnected is still on, and it's going to switch off after 5-second delay. Okay, so that's kind of like it, this delay. So meaning when you're working out of range of your battery dries, you have a kind of a few second delay before everything switch off. But you can also increase the capacitor there, or increase the resistor, so it can discharge more slower, and then you have more time of more milliseconds, of more seconds to switch things off. Okay, but so this is gonna be always transmitting to the receiver there. You put the battery on, transmit automatically. Okay, and then let's say you work out of range and you cannot transmit anymore to the receiver, you can still activate, switch on things on and off using the manual mode. Okay, this is now the manual mode. Press it again, goes off. Now let's talk about the relay here. Okay, if I zoom a little bit to the relay, so if I zoom to the relay here, you can see here you have like a small symbol, a switch, and then you have a 10 amps, and then you have a 250 volt. Okay, so I'm going to show you a formula how to calculate how big load you can switch on with that relay. Okay, so what we have here now, it is I'm going to show you the formula to calculate the power. So get there a little bit. So we have here P, okay, is equal to I times V. P stands for watts, this I stands for amps, V stands for volts. Okay, oops, sorry, it's one T there, stands for a volt. So we already know how many amps the relay contains. So it can switch up to 10 amps. Okay, the voltage was about this times 250. Okay, 250. So, and then this is gonna give us about 2500 watts. So the relay can switch loads up to 2500 watts. Okay, but I have to say I'm living in Belgium. In Europe, we use around 230 volt here. Okay, so that's meaning now it's 10 amps times 230, we get 2300 watts. So this is what the relay can switch here. It can switch here in Europe or here in Belgium. We're not using 250, it's only 230, so that's what we mainly use, and that means it's gonna switch 2300 watts. And most of the home appliance actually it's about this size, 2300 watts, switching like a big heaters and stuff like that. This kind of amount used, but the other things they use less than that. So the relay there is suitable enough to switch on things around home on and off. And the relay, how it's working is itself is like this. Okay, and then here we have a switch like so, and then we have our lamp here. Oh, sorry about that. Again, like so. So we have our lamp here, and then we have our lines coming in. So we have natural, we have a neutral line, and then we have a live wire. So this goes here, and then here goes over there, and then this one goes over there. So you can see, so when you power the relay, you're gonna pull up this lever here and close the circuit, so then the AC is gonna go through. So it's just breaking it, and then I mean opening and closing it. So that's how the relay is working inside there. And then we have also got a diode there, okay, to prevent the voltage and going back to the transistor, otherwise you're gonna damage there. Okay, so but this is how it's working inside the relay. Okay, so that's all about it now, about this circuit. You can see it's working really nice. Press it again, it goes off, and the voltage also the voltage is nice. It's 10 volts, about 0.5 milliamps on standby, and when it's working is about 0.54 milliamps. Okay, so that's all about it. So I'm designing all this on a deep trace, and then going ahead and milling on a CNC machine. Okay, so we have a switch there. I press the switch again, it goes off, and then I can also use the transmitter and it turns on automatically. Let's say if I had a switch here, so I press the switch, turns on. Okay, if I release it, it turns off, and you can see here the LED lighting here, because it's now this is a battery cell. It's about 3 volts. I think it's lower than that. Now the LED is lighting, indicating that the battery has to be changed. Okay, but so that's all about the circuit. Okay, so but I'm gonna also show you another circuit here I'm gonna add. Okay, because this one here is AC. It is a transformerless power supply. So not transformer, only electronics of a component. So we have a fuse, we have an excited capacitor here, 470K as a bleeder. Okay, we have a bridge rectifier there, then a 12 volt Zener diode and a LD indicator when the power is here. I'm gonna show you a table here. Okay, so if you want to choose the correct excited capacitor here, then you can see how much current this thing can give. So for example, the first one here can give up to 8 milliamps. Okay, and then this one here we have 220 milliamps and go and all the way on up to 100 milliamps. Okay, but as you see, our circuit here is not really using much, so I think I'm gonna go ahead with this one here. This is kind of okay for me. So just a small table to see excited capacitor, how much a current can give. Okay, so this I haven't made it on a breadboard, but I'm gonna just make it on a deep trace. Okay, so we have this one here, and then we have our receiver over there, and then we have our transmitter as well. Okay, so guys, that's all about it. So I see you to the next level, next step on making on a deep trace and going ahead and milling it as well.